Unit 6, Video Lecture 1, Molar Review. Before we start talking about the mole and molar mass, let's review a little bit about the information contained for us on the periodic table. If you recall, the top number 6 is our atomic number. Our atomic number is equal to the number of protons found in an element. It is unique to each individual element. The 12.01 is our atomic mass. This is the weighted average of all of our isotopes. So this includes our isotopes. And it's going to be this number that we're going to be working with when we start to look at formula mass. Formula mass is simply the mass of all the atoms in a formula. So if we look at water, the 2 tells us that there are 2 hydrogens. So if we look at our periodic table, and we find hydrogen, hydrogen has a mass of 1.01 AMU. So, considering that we have 2 atoms of hydrogen, we have 2 atoms at 1.01 AMU. Oxygen has a mass of 16 AMU. So we take 2 times 1.01 plus 16.00, and we get a mass of 18.02 AMU. Let's look at another compound. Copper 2 hydroxide. Well, looking at our periodic table, we can look up copper, see that it has a 63.55 AMU mass. Now, looking at our hydroxide, remember this 2 on the outside of our parentheses is distributed to both the oxygen and the hydrogen. So that means that we take 2 times 16 plus 2 times 1.01. So we take 63.55 plus 2 times 16 plus 2 times 1.01, and we get a mass of 97.57 AMU. That's the mass of the formula, copper 2 hydroxide. So, we talked in Unit 1 about the mole, and we know that the mole is the SI unit for the amount of substance. It can be used to tell us a number of things. Okay? It can tell us how many of something is present. And to do that, we use Avogadro's number. We can also use the mole to tell us the mass of something. For this, we would use molar mass. Remember, the mole is abbreviated MOL. So if we look at how much of something's present, we can determine the number of atoms. So atoms of carbon, helium, etc. We can say the number of particles, a much more general term. We can say a number of formula units. This would be used if we're using ionic compounds. Or molecules. our covalent compounds, and our diatomics. Each one of these can be related to the mole. And they all have the same number. There are always going to be 6.02 times 10 to the 23rd particles in a mole. So let's take a look. If we're talking about neon, the formula for neon is Ne. So how many neon atoms would be in one mole? 6.02 times 10 to the 23rd. Neon atoms in one mole. What about oxygen molecules? Well, oxygen, O2, would also have 6.02 times 10 to the 23rd. Water, H2O, a water molecule, there would be 6.02 times 10 to the 23rd water molecules in 1 mole of water. Sodium chloride formula units, because it's an ionic compound, would still have 6.02 times 10 to the 23rd. So we can use Avogadro's number to determine the number of particles in a mole. We also can use the mole to determine the mass of 1 mole of a substance. Now, molar mass is abbreviated capital M. It's important to remember that molar mass is the mass in grams. What's the mass in grams of 1 mole of a substance? So it's important to understand that molar mass is a relationship. It's some number of grams equal to 1 mole. And since it's a relationship, we can write it as a conversion factor, where we'd say some number of grams over 1 mole, or 1 mole over some number of grams. So let's take a look. Calcium. The formula of the calcium atom is Ca. The formula mass of calcium, if we look up on our periodic table, is 40.08 AMU. This means that the molar mass, the mass of 1 mole of calcium, is 40.08 grams equals 1 mole. We can also write that as 40.08 grams per mole. Chlorine. Chlorine's a diatomic molecule, so it's Cl2. That means that we have 2 atoms of chlorine. Each chlorine atom has a mass of 35.45. So the formula mass of Cl2 is 70.9 AMU. So the molar mass of chlorine is 70.9 grams per mole. Water, H2O, has 2 hydrogens and 1 oxygen. So the formula mass of water is 18.02 AMU. So the molar mass of oxygen would be 18.02 grams per mole. Sodium chloride, NaCl, combines sodium 22.99 and chlorine 35.45 to give us a mass of 58.44 AMU. This means that the molar mass of sodium chloride is 58.44 grams per mole. So let's look at a sample problem. During photosynthesis, plants produce glucose, C6H12O6, which is a sugar that we use to undergo cellular respiration. What's the molar mass of glucose? Well, first we need to determine what elements are present. So if we go through and take a look, we have 6 atoms of carbon, we have 12 atoms of hydrogen, and 6 atoms of oxygen. So we take our 6 atoms of carbon, so 6 times 12.01, our 12 atoms of hydrogen, and our 6 atoms of oxygen. So we take our 6 times 12.01 plus 12 times 1.01 plus 6 times 16, and it tells us that our molar mass of oxygen is 180.18 grams per mole. Practice on your own. Pause the video and determine the molar masses of the following. I like to think about molar conversions and use a map to help me get from where I'm starting to where I want to go. So right now we have 3 islands. We have mass island, we have mole island, and we have particle island. Particle island is made up of particles, formula units, atoms, and molecules, or essentially anything that we want it to be. So the blue backdrop obviously means that these islands are surrounded by water. So if we want to drive our car from mass island to mole island, well, we don't have a car that can drive on water yet. So we're going to need to take a bridge. And to go from mass island to mole island, we're going to use the molar mass bridge. That's where we're going to calculate the molar mass of our substance based off its formula mass, and then do our calculation. If I want to take my car and go from mole island and drive to mass or particle island, or start on particle island and drive to mole island, I'm going to take the Avogadro's number bridge, and I'm always going to use that 6.02 times 10 to the 23rd equals 1 mole. So let's practice. How many atoms of mercury are there in 2.5 moles of mercury? Well, let's take a look at what we're given. As you can see, we're given 2.5 moles of mercury. We want atoms. How many atoms? So from our map, we're starting on mole island and we want to go to atom island. In this case, we would use Avogadro's number. So the first thing we do is start with what we're given. 2.5 moles of mercury. Notice here, I'm including 3 things. I'm including the number, I'm including the unit, and I'm including the substance. We're going to need all 3 of those things in our upcoming chapters, so we might as well get used to writing them now. So now that I have my 2.5 moles of mercury, I'm going to draw my conversion and use Avogadro's number. Remember, Avogadro's number says 6.02 times 10 to the 23rd. In this case, atoms of mercury is equal to 1 mole of mercury. So, what do I want to cancel out? I want moles of mercury to cancel out. So I'm going to take my 1 mole of mercury and put it on the bottom. This means that 6.02 times 10 to the 23rd atoms of mercury goes on top. Now, let's enter it into the calculator. Using our calculator, we're going to plug in our 2.5 times 6.02, and we're going to use our E function. To get to our E function, we're going to hit second, and then the inverse button. Because if you notice, above the inverse, there's the EE. So, EE will display as just one capital E, and that's going to take the place of our times 10. So our keystrokes here should 2.5 times 6.02, our second button, the inverse button, so that we get our EE, 2, 3. So here if we take 2.5 times 6.02, and again we're using that E function, 2, 3, we get a fairly large number. So let's put this number into scientific notation. .505 times 10 to the 24th. Our last step is always going to be to round significantly. Here we have two significant figures, the 2 and the 5. Our second significant figure is this first 5. So we look directly to the right. The 0 tells the 5 to stay a 5. So our final answer is 1.5 times 10 to the 24th atoms of mercury. So, how many molecules are there in 6.25 moles of ammonia? Well, we're given 6.25 moles of ammonia, and we want molecules of ammonia. So here, this time, we're starting on Mole Island, and we're trying to go to Molecule Island. To do this, we use Avogadro's number. 6.25 moles of ammonia. I'm going to use Avogadro's number, which is still 6.02 times 10 to the 23rd. In this case, molecules of NH3 is equal to 1 mole. So I will put my 1 mole on the bottom because that's where I want it to cancel. And 6.02 times 10 to the 23rd molecules on the top. So again, I'll make sure that I use my second inverse button. 6.25 times 6.02 times 10 to the 23rd, 3.762 times 10 to the 24th. This time I have 3 significant figures. the 6, the 2, and the 5. So my third significant figure here is the 6. So I look to the right, and the 2 tells the 6 to stay a 6. So my answer should be 3.76 times 10 to the 24th molecules of NH3. So let's take a look. 30 grams of H3PO4 is how many moles? We're given 30 grams of H3PO4. We want moles of H3PO4. So this time we're going to start on Mass Island and try to go to Mole Island. So to do this, we're going to need to use our molar mass bridge. So here we can't just use that 6.02 times 10 to the 23rd. We actually have to look at the molar mass of H3PO4. H3PO4. We have 3 hydrogens plus 1 phosphorus. Now, if we don't know phosphorus's molar mass, or atomic mass off the top of our head, let's look back at our periodic table and see that it's 30.97. So 30.97 plus 4 atoms of oxygen. This gives us a molar mass of 98.00 grams per mole. So now we can take our 30 grams of H3PO4 and convert it. I want to get rid of grams. So looking back at my molar mass, I'm going to take my 98.0 grams and put it on the bottom. And I'll use my 1 mole and put it on the top. Remember, molar mass is always to 1 mole. So here I take 30 times 1 divided by 98, and I get 0.306122. How many significant figures do I have? Well, the 3 is the significant. What about the 0? Well, it's a trailing 0. And trailing zeros need a decimal point. Because of the decimal point, we have 2 significant figures. So our second significant figure in our answer is the 0 between the 3 and the 6. So we look directly to the right, leaving us as an answer of 0.31 moles of H3PO4. 5.6 moles of C6H6 is how many grams? Well, we're given 5.6 moles of C6H6. We want the mass of C6H6. So this time we're starting on Mole Island and we want to go to Mass Island. However, our bridge is still the same. We're still going to use our molar mass bridge. What's the molar mass of C6H6? Well, we have 6 atoms of carbon and 6 atoms of oxygen. So 6 times 12.01 plus 6 atoms, 6 times 1.01 gives us a molar mass of 78.12 grams per mole. So we start with our 5.6 moles of C6H6. And what do I want to cancel out? I want to cancel out moles. So I'm going to put my 1 mole on the bottom and put my 78.12 grams of C6H6 on the top. When I take 78.12 times 5.6, I get 437.472. So I got to go back and check my significant figures. 5.6 has two significant figures. So here, my second significant figure is the 3. I look to the right, and the 7 tells the 3 to become a 4. So 437 rounds to 440. Notice, no decimal point. We don't want that 0 to be significant. Grams of C6H6. Even though there's more time, you can stop watching, or you can continue on for additional practice problems. Additional mole to mass, mass to mole problems. If we want to convert, looks like we didn't put a number here. So let's choose 25 grams. If we want to convert 25 grams of iron 3 chloride to moles of iron 3 chloride, we're starting on mass island and we want to work to mole island. So we're going to use our molar mass bridge. The molar mass of iron 3 chloride. Iron has a mass of 55.85 plus 3 atoms of chlorine at 35.45. This gives us a molar mass of 162.2 grams per mole. So I'll take my 25 grams of iron 3 chloride. I want grams to cancel, so I'll put 162.2 grams of FeCl3 on the bottom and 1 mole on the top. When we do this, we get an answer of 0.15413, etc. Well, 25 has two significant figures, so I am rounding to my hundredths place. I look to the right, the 4 tells the 5 to stay a 5, so my final answer is 0.15 moles of FeCl3. 564 grams of oxygen is how many moles of oxygen? So again, we start on mass island and we want to go to mole island. So we're going to use our molar mass bridge. One thing here that we have to keep in mind is that oxygen is a diatomic molecule. So its formula is O2. Since its formula is O2, we have 2 atoms at 16 for a molar mass of 32.00 grams per mole. So we start with our 564 grams of oxygen, and I want grams to cancel out, so I'll put 32.00 grams on the bottom and 1 mole on the top. This leaves me with 17.625. Well, 564 has 3 significant figures. My third significant figure is the 6, so I have 17.6 moles of oxygen. Let's look at a couple conversions going from moles to mass. I'm starting on mole island, and I'm trying to get to mass island. So I'm still going to use my molar mass bridge. So the molar mass of calcium, if you don't recall, let's look it up. Calcium has a molar mass of 40.08. So we set up our problem, 8.96 moles of calcium. This time I want moles to cancel out. So I'm going to put my 1 mole on the bottom. I'll put 40.08 grams of calcium on the top. So now I'm going to take 8.96 times 40.08 and get 359.1168. 8.96 has 3 significant figures, 1, 2, 3. So my answer is 359 grams of calcium. 5.89 moles of sodium hydroxide. Well, we have to, in order to get the molar mass, we're going to need to write the formula. So sodium has a charge of positive 1, hydroxide has a charge of negative 1. If we crisscross our signs, our charges, we have Na minus 1, OH plus 1. We drop the signs, Na1OH1, our formula is NaOH. So, the mass of sodium is 22.99 plus the 16 for oxygen plus the 1.01 for hydrogen. This gives us a mass of 40.00 grams per mole. So, starting with 5.89 moles of NaOH, I'll put my 1 mole of NaOH on the bottom, and my 40.00 grams of NaOH on the top. So I take my 5.89 times 40 and get 235.6. I have 3 significant figures here. So my answer should be 236 grams of sodium hydroxide. You can stop the video here if you're done with additional problems, or you can go back and join our lecture previously started. Additional mole to particle or particle to mole problems. We want to look at 9.3 times 10 to the negative third moles of SNO is how many molecules? Well, since we're starting with moles and want to go to molecules, we're going to need to use Avogadro's number, which recall is 6.02 times 10 to the 23rd, in this case, molecules of SNO. And that's equal to 1 mole. So we take our 9.3 times 10 to the negative third moles of SNO, and we'll put our 1 mole of SNO on the bottom, and 6.02 times 10 to the 23rd molecules of SNO on the top. So we'll type in 9.3, and remember, we're going to use that second button and the inverse to get that capital E. So we're going to use E negative 3 times 6.02 times 10 to the 23rd. And we'll see that we get, in scientific notation, 5.5986 times 10 to the 21st. Well, 9.3 has 2 significant figures, and our second significant figure is the 5. So we look to the 9 tells the 5 to become a 6. So our answer is 5.6 times 10 to the 21st molecules of SNO. We're going to use Avogadro's number again because we're still going from mole island to atom island. So we'll take our 2.35 times 10 to the 5th moles of neon, and we'll put our 1 mole of neon on the bottom and our 6.02 times 10 to the 23rd atoms of neon on the top. Remembering to use our second inverse function, we're plugging in 2.35 second inverse to get that E, 10 to the 5th, times 6.02 second inverse for the E, 23. We get 1.4147 times 10 to the 29th. 2.35 has 3 significant figures, and our third significant figure here is the 1. So we look to the right, the 4 tells us to keep the 1 the same, so our answer is 1.41 times 10 to the 29th atoms of neon. If we want to practice going the other way, we have 8.65 times 10 to the 26th molecules of neon, of ammonia. So here we're going from molecules to mole island. We're still going to use Avogadro's number, and we're still using that relationship 6.23 or 6.02 times 10 to the 23rd molecules equals 1 mole. So we take our 8.65 times 10 to the 26th molecules of ammonia, and here we're going to put that on the bottom. We're going to put our 6.02 times 10 to the 23rd molecules on the bottom, and our 1 mole on the top. So we take 8.65, we'll use our second inverse function to get that E to 26. Now we're going to multiply by 1 and then divide by 6.02 times 10 to the 23rd. This gives us 1436.877. 8.65 has 3 significant figures. Our third significant figure is the 3. So we look to the right, and the 6 tells the 3 to become a 4. So 1,436 rounds to 1,440. Again, notice, no decimal point. And our units left are moles of ammonia. 8.96 times 10 to the 12th molecules of carbon. Actually, this should be atoms. I apologize for that. So we want moles, so 1 mole will go on the top. And we want 6.02 times 10 to the 23rd atoms of carbon on the bottom. 8.96 times 10 to the 12th times 1 divided by 6.02 times 10 to the 23rd gives us 1.488 times 10 to the negative 11th. We have 3 significant figures in our given, so we'll round to the first 8. The 8 tells the 8 to become a 9, so we have 1.49 times 10 to the negative 11th moles of carbon as our answer. You can stop the video here, or you can click your link to go back to the lecture already in progress. Additional problems for determining molar mass. Remember, to determine molar mass, we take the mass of all atoms present, and our units are always grams per mole. So we have 2 atoms of hydrogen, so it's 2 times 1.01, and 1 atom of oxygen, which has a mass of 16. This gives us a molar mass of 18.02 grams per mole. Sodium carbonate. Here we have an extra step of determining the formula. Sodium is an Na positive 1. Carbonate, the polyatomic ion CO3, is a negative 2. To determine our formula, the first thing we do is to crisscross. So Na minus 2, CO3 plus 1. We next drop the signs and then reduce. So our formula is Na2CO3. So we have 2 atoms of sodium at 22.99 plus carbon at 12.01 and 3 atoms of oxygen at 16. This gives us a molar mass of 105.99 grams per mole. You can either stop watching or return to your video lecture that was currently in progress.